Sí, está. Si algunos se van a revisar. No existe PI aquí, solo sí.
Tienes que ver con Rafael.
Okay, hi everyone. I think we have a critical mass of people that allows us to start. So let's start today's class. Okay, so yeah, sorry I was not able to stick around at around the end of the contest yesterday because I had a meeting shortly after. But I don't know, just to gauge some reactions. So for example, who does think that the contest was too easy? Okay, who thinks it was too hard? Great, who thinks it was okay in difficulty? Okay, kinda good. Okay, I'm happy about it, though I think today's contest will be a bit more difficult. Sorry about that. I mean, I don't want to... I think it's not extreme or something, but just don't be surprised if it's just slightly bit more difficult than yesterday's. Okay. Otherwise, what are your opinions in general? Did you like the problems?
Yeah.
Yeah, they were okay. Okay. I was thinking about how we should approach. I actually don't really want to discuss the whole problem sets on each day because it takes a lot of time, and I think you already discuss a lot of problems between yourselves, and problems which were solved by half of the teams or something like that maybe not worth to discussing too long, because you can also talk to each other or ask me out of class about a solution if you are interested. I will focus on the few most difficult tasks, I think, on each day. So looking at the number of solves, I was actually surprised that the data structure one is not going to be among them. I mean, okay, it didn't require any very unknown ideas, but I expected it to be a bit more difficult to implement or to solve. So the four most difficult ones actually included, which I wanted to talk about anyway, this game on the plane task. Okay, just so if you encountered an issue during solving this task, actually almost all of the problems were from the Hungarian sub-regional ICPC contest. This problem was one of the exceptions. I'm not sure if this problem was actually used at a contest. We usually use this problem in a training judge, so I just copy-pasted it. So some of you I saw encountered some problems when trying to squeeze the time limit. I hope it was not super bad. I didn't spot there might be an issue because our specific implementation of the almost all matching algorithms, including Hopcroft-Karp, with which some teams were struggling with, passed, and I didn't spot that there might be an issue. So sorry if you needed to squeeze it a bit, but it was maybe doable. Okay, so in this problem we are given some points selected on the plane. And what we would like to do is there are two players. The first player can choose a starting position, and then the players move alternatingly. And the one who cannot make a move loses the game. And we had to find all the winning positions, in the sense that all the positions where the first player can put the marker and force a win. Okay. Is everyone familiar with the problem statement? great. Okay, so the main idea to solve this task was to recognize that these points form if you think about the possible moves, then actually these points form a bipartite graph, because if you just look at the possible transitions, the possible moves you can make from each of the points, you can notice that if you mark the points according to like a chessboard pattern, an alternating pattern, then you can see that from the marked positions you can only move to unmarked, non-marked positions, and vice versa. So if you use this checkerboard or chessboard pattern, you can immediately see that this separates the points into a bipartite graph with respect to the available moves. Okay. So you might, if just thinking about yesterday's class, you might immediately think about whether this problem has any connection to the maximum matching or the minimum vertex cover problem, since it is a bipartite graph, and you might immediately get some ideas that, okay, if I have a maximum matching, maybe some strategy could revolve around like waiting for a move, then move around, then move on using a matched node or something like that. So you can get some basic ideas that matching might be a key point in finding a winning strategy for any of the players. Okay, so actually the very first observation I think we can make is if you consider a maximum matching, in this graph, and then you consider a position. Okay, let's just pick a maximum matching here. Okay, I think this should be one. Yes. Okay, so there are some positions that are very easy to see that must win the game if you put if you select them as the starting position. These positions are the ones that are actually not part of the matching, the unmatched nodes, right? If you put I don't know what was the story, so if you select an unmatched node as a starting position, then you can force a win, right? Because if there are no edges from this vertex, then you immediately won. The other player cannot make any move. And if there are edges, they are unmatched edges. They are not part of the matching. So the opponent must move along an edge that is not part of the matching. And then you can see that you always arrive at a vertex which has an adjacent edge which is part of the matching. So, for example, if he moves here, you can just move along using the matching. Or if you yeah, there are no points like that. Okay, can add maybe one more here, though I'm not sure if this works. Probably yes. Okay, so then the opponent moves, you move along an edge that is part of the matching, then the opponent might have extra moves, but he cannot use the same edge which is part of the matching, so he once again moves along an edge which is not part of the matching, and you can repeat the same process. Why is it true that you always can move with an edge, or you always have an edge available to you that is part of the matching? Why is it true?
Because it will be on.
Otherwise there would be an augmenting path, because that would mean that in the last move the opponent moves along an edge that is not part of the matching and you are stuck, so there is no edge adjacent that is part of the matching, it means that since you started moving along an edge that is not part of the matching and the last move was also along an edge that is not part of the matching, then you made a sequence of moves on an augmenting path, and so that's a contradiction. Okay, but the question is, are there any more winning positions? So are there any points that are actually matched to something, but still if you put the if you select it as a starting position, you can force a win? Okay?
Yes.
Yes? Which are these points? Can somebody tell me?
Points that are not on all max matchings.
Sorry?
Points that are not on all max matchings. Like there is a max matching which doesn't include it.
You mean there are any max matching that doesn't include them? Yeah. That makes sense. I mean, that's definitely true. But is there maybe an easier way to find them, select them? Because algorithmically, it might be tricky to decide it out of the box whether a point is part of any maximum matching or not. Yes?
If there is an alternate path between a matched node and the matched node, then you can swap the edges and the matched node becomes matched.
Yes, yeah, that's correct. Maybe I will explain the same thing using the terminology from yesterday. If you think about it, when we constructed the min vertex cover, so actually there's a good connection to that problem here. When we constructed the min vertex cover, we actually can remember that we considered these structures where we start from an unmatched node and then move along an edge which is not part of the matching. Okay, and then if any of these are matched, then we use the matched edge and so on. Okay, remember this from yesterday. So you can immediately spot that in these graphs, we already proved that this is a winning position. Okay, actually that's what we just discussed. But otherwise, we also proved that the depth of this structure is always odd. Okay, so it also means that these positions and these positions, which are actually vertices that are matched to something right now, are also winning. Okay, why are they winning? Because if the opponent moves along an unmatched edge, then we can repeat the same strategy, move along an edge which is part of the matching, and whenever it's possible. Okay. And otherwise, if the opponent chooses to actually use the edge, which is part of the matching, then we can always make a step towards the root. And we know that at the root, we will win, because we will be the ones using an edge which is not part of the matching in the last term. Okay, so actually, for example, if you construct a max matching and you run the same algorithm that you use to select the min vertex cover, you can immediately select all the winning positions. Yeah, of course, if you proceed this way, just be careful if there is a component like this. Okay, so of course these are all losing positions. We are only. I mean, you automatically exclude it if you just run this thing from the unmatched vertices, because then you never find something like this. But this is like a pitfall which you must avoid. Okay, is it clear? Any questions? Okay, great. Okay, the next one, I think it's, yeah, in the order of number of solves, it was lighthouse lamps. Okay, so I didn't really check all the solutions that you submitted to this problem. There are more than one ways to solve it. I will explain one possible idea. Yeah, the task itself was that we are essentially given a tree. Okay, and some procedure. So each node can have two possible states. Each of them has a lamp, which is either turned on or off. So each node has a state which is either, let's say, 0 or 1, off or on. And what we do is we visit the vertices in some order, and whenever we find that a lamp is turned on, we send a signal which flips the state of every node on the path to the root, but it does not flip the state of the current node. Okay, and we are given some number of starting configurations, and we are also given some number of iterations. So we don't do this just once, we do this some k number of times. This process when we go through all the vertices and send a signal whenever a lamp is on. Okay, and we want to find, after performing k iterations, the state of the lamp in the root. Okay, everyone is familiar with the statement? Yeah. Okay, so I think the difficult part of the problem, well, there might be two difficulties. The first one immediately at the start is if you really want to somehow keep track of whether a lamp is currently on or off, it can be a bit tricky to do so. It's convenient to come up with different formalization that essentially does not change the state of the lamp, but replaces it with a more simple operation. One possible way to do this is to think about the states similarly to, as I explained, as bits, zeros or ones. Or not necessarily bits, you can also think about them as numbers. And an observation which can help you to solve the task is the following. Instead of doing flips, you can think about the operation as if we visit some node. The node actually adds its value to its parent, and not just its, to its parent. Yeah, I was right, okay. And then, I mean, no, I wasn't right. Actually, it adds its value. I'm sorry, it adds its value to all of the nodes on the path to the root. Sorry about that. So you may think about it, for example, when you visit this one, that it adds its value to the root. So this becomes like this. And when you visit this one, for example, then what happens is you add the value of this one to all of its ancestors. So this becomes 2 and this becomes 2. Nothing else changes. Okay. So we can consider these additions because actually why this observation works or why we can replace the operation with this, the reason is in the end we are actually interested in the parity of each vertex. It simulates the state of the lamps by checking the parity of the number in each vertex. Okay, see here, we added 1, so this changed from even to odd, so now it's turned on. And here what happened is we added 1 to all of the ancestors, so this became 2, which is even, so it is turned off from now, and the root also switched states. It was turned on, but now it's turned off. Okay, Is there anyone who doesn't understand this idea? Why does it works? If yes, just ask. Okay, so after finding this representation of the operation, we are in a much more comfortable situation, I would say, because actually now we can try to find we should find the sum in the root after performing the operations some number of times. Okay. So how to do that? You can see that it still becomes tricky if you perform the operation multiple times. If you needed to do it just once or something like that, it's simple. But if you do the operation multiple times, it's still an issue that the values in each node changes, and then you add a different value to the ancestors in the next step. So what you can do instead is a relatively common idea. Try to keep track of the original values, the original zeros and ones. In the sense that, okay, initially this one has a value 1, and later on we can think about, for example, this value 2 here as 1 by 1, 1 plus 1, where 1 was the original state, and this one came from here. So we keep track of the number of copies of the same bit, essentially. Okay, so this 2 is 1 plus 1, but 1 came from this, so this is a copy of this bit, and the other one is the copy of this bit. Right? So one feasible way to solve the problem is to enumerate the number of copies of each initial bit, if that makes sense. Okay, and we, of course, just need to find the number of each bit in the root, of course. But in order to find the number of copies of each bit in the root, you also need to know the number of copies that exist at other places. Okay, so how to do this? How to count occurrences of the same bit. Okay, you can come up with a clever argument out of the bat, or you might try to observe what is actually happening, and then and then you can actually spot the pattern very easily. So, for example, if now we just have to think about one particular bit. So let's just focus on how the occurrences of this bit changes in the vertices. We know that this bit only occurs on this path, nowhere else, naturally. Okay, so after one step, we have something like this. After 2 steps, we have this, right? Why? Because here we add 1, here we add this one, and this one in the second term, and to the root we add this one, and this one over our path, right? You can also say that, okay, after one iteration, each node will contain the sum of the values in its subtree. If you wish, you can also say that. Okay, so if you do this, you might spot a pattern. That's a perfectly feasible way to do it. I don't know if you recognize where these numbers are coming from. They are from some row of the Pascal triangle, right? These are some binomial coefficients, if you want to say that. Okay, so you might come up with the formula that if, so it's, you can see that we are actually interested in this particular value. So you might come up with the formula that it actually depends on the depth of the node, the distance to the root, okay, and the value of k, of course. Yeah, you see in each step we descend one row in the Pascal triangle, and we always get the what is it, 0, 1, 2, 3, the deed, the number from the position d in the given row. Okay, so the formula is therefore something like what is it, k plus d minus 1 over d, I guess, something like this. Okay.
What is K and D specifically?
Yeah, sorry, it was, I took them from the statement, but I mean not D. So D is the depth of the node that we are analyzing, and K was the number of iterations. So, 0th or first, I don't know. 8. Okay, I think it's K minus first, but yeah. Okay, though actually we are not interested in this number, we are just interested in this number modulo 2, which makes the code much more simple if you wish. Okay, is there anyone here who solved the problem? Okay, what was your approach, if you would like to explain?
Like, you can see that applying the operation once is like multiplying the start state by a matrix as like the ancestry matrix. And then you want to exponentiate this matrix by k minus 1. So you can come up with like exponentiate the ij entry of the matrix exponentiated k times is equivalent to go down from I to j. Going down, I mean like just going to a child, or like 2 times, any number of times, and you can like select the same node. So like you get a k tuple. This is the node I, this is the node j, and then the next node can be some child of node I. So this is just the stars and bars. If you see, like instead of selecting nodes, selecting how many edges you go down each time. So it's equivalent to that.
Yeah, that's what I wanted to say. It's an equivalent solution, very nice. I also wanted to mention this, so I'm happy that somebody actually found it. You actually don't necessarily need to do the combinatoric part. You can think about the operation at some point over your solution as some form of linear contribution or a linear transformation of some sort. So you might, for example, calculate or look at the contribution of this particular vertex by writing a matrix where you can immediately see you have to take into account all of the nodes towards the root. So you can just do this transformation as a matrix multiplication, right? Where the rows and the columns correspond to how many occurrences of the bits in one node transfer to the other one. So for example, in each iteration, the contribution of this, it just contributes 1 to each of its ancestors. So that would be something like, it gets added 1 times to this, 1 times to the parent, and 1 times to the root. And it also maintains its own value. So, yeah, it will be something like this. Okay, and you can think about the others in the same way. You will get a matrix with this kind of structure, I think. Okay, and then you somehow solve the problem. Actually, maybe an even more cheesy way to do it is to represent this transformation as a polynomial. Okay, at each node you contribute, the degrees of x will correspond to the number of levels you lift the current value. So you keep it on the same level, you lift it once, you lift it twice, and so on, and you lift it d times. This can also be used to represent one transformation, and then you can just compute the kth power to see the coefficients which give you the contribution of this to each of the nodes above it. And actually you don't need to do this for every depth independently. You can do this for all depths all at once if instead of d you use here the maximum depth. The reason behind it is if the tree is deeper, we don't care if the depth of a node is smaller, it just means we don't have to lift max d levels, we only need to lift less number of levels. So this is also like a cheesy way to skip the combinatorics. Okay, any questions? Okay, great. Okay, next problem. Get some rest. Okay, in this task, we essentially have some form of a simulation problem. We have a relatively simple assignment problem. We are given like a stupid algorithm which tries to solve it, and we need to simulate or find the outcome of this stupid algorithm, which is also very slow in the given form, so we have to somehow simulate it fast and efficiently. Okay, so you can immediately see that the input is almost a tree structure because there are hotels. Each hotel can send beds to one hotel with lower index, which means to some lower quality hotel. So if you just take that part into account, that would mean something like you have a tree structure, but you can also send beds from this hotel to some other hotel, so it would actually have one cycle. But only one cycle like this exists according to the statement. Okay, and the problem is we have some balance in each node, which represents whether we have extra number of beds or lack of beds in them. So each of them has some A0, A2, A3, A4, A5, A6, A7, A8, some number associated to it. Okay, and the algorithm which we perform is we always select the greatest A value, take all of them, so set this to 0, and add this value to the parent. So we transfer every bed from one hotel to the assigned hotel, and there we distribute beds. So we add the two numbers and then repeat. Okay. Okay, are you familiar with the statement? Okay, the question is, you have to find whether this algorithm actually achieves a state where there are no negative numbers, where there are no missing beds, and you have to find the minimum number of, the first step, the first occurrence of this state. And it might never happen, then you have to report that it never happens. Okay. So I don't remember how much it was explained in detail in the statement, but the part that it doesn't happen, so it doesn't solve the problem, can happen two ways, right? One way it can happen is the algorithm actually terminates, so there are no more steps to be made, but we are left with a negative number. Terminates, exists negative number, then it didn't solve the problem. And the other The other case when it doesn't happen is if the algorithm runs infinitely, because it might happen that we keep transferring some bed over this loop, but there is some negative number that never gets removed. Iterates forever, but there exists some negative that doesn't get removed. Okay. Otherwise, it solves the problem. Sometimes it might terminate, but usually it doesn't have to terminate. So it might run infinitely, though maybe the statement said it terminates immediately when the problem was solved. It doesn't really matter. You might think about it as if it terminates infinitely, but the problem becomes solved when there are no negative numbers left. It's equivalent. It doesn't matter. Okay, so we need to somehow simulate it, and you might need to think a bit, but you can realize that the given algorithm, if you do it in a brute force way, like even if you select the bed to move efficiently in some data structure, it can still be slow. Okay, you can construct examples where it requires like n square steps until you can decide whether it's over or not, because it might happen that from some subtree you only manage to move the beds out one by one, and then those beds get stuck somewhere, and so then each bed from a subtree would make a long way until it finds its correct position. So the brute force simulation doesn't work. It's not immediately obvious, but you should realize that or submit a solution and get a time limit. But anyway, so how to do it more efficiently? Okay, so an observation we can make is if we move beds from a hotel, then at the time when you move some beds out, the number of beds will be 0 right after. Okay, later on, for some of the hotels, some beds may appear again in the same hotel. But in almost all cases, if you move the beds out of somewhere, let's say you moved the beds out of here, so this becomes 0. In almost all cases, whenever you move beds to this hotel, then in the very next step of the algorithm, you immediately move them out. The question is, why is it true? Is it true at all? And what do I mean by almost always? Because it might not happen. Yes?
If on the path you're taking the beds, there are always positive values, you must always remain the maximum.
Yes.
And walk it.
Yes, exactly. If you move the beds from here to here, that means you moved from a larger index to a smaller index. If this was the largest stack of beds, then it remains the largest stack of beds, so you immediately move them forward. Excellent. So that's why you can assume that it stays 0, or at least you immediately need to move the beds forward from it. Okay, what is the exception? Yes?
If there is a negative amount of beds, you can, when you walk there, you may not be the maximum.
But I claim that this has zeros. So if this already has zeros, then after that you can always skip through that. So what is the only exception? There is just one particular node where this negative thing can happen.
Yeah, I think the exception when there are more more vertices with the same amount of bed, they are choose someone random. Or not? I don't remember the
Not really random, because if you have the same amount of beds, you always move the one with the lowest index.
okay.
So if you move this to the 0, then in the next step you will need to move it once again. Because the number stays the same. A0, move there, A0, the same number, the index is lower, you must move it again. So in that sense, you can simulate two steps at once. If you know that this is 0, then you can immediately put these beds here and say that I did two steps. And the same is true for almost every vertex. There is actually just one exception. When you do this. If you have 0 here, the same doesn't hold. If you move beds from here to there, you are not guaranteed to be able to move them in the next step, because there might be the same amount of beds somewhere else. So this node is special. Here we shouldn't do this like speed up by skipping the zeros. We should always consider a step where a stack of beds return to this hotel. But other than that, after every step, we can optimize. After every step, because in each step, you actually create a node which contains 0 afterwards. Any step you make one of the nodes empty and move the beds, right? Okay, so if we move beds from a hotel, so it becomes 0, then we can skip this hotel from now on and move to its parent adding +2 steps. Okay, every step creates a node with the value 0. And of course, this observation can be applied not to just one step, but to multiple steps. So if you already have a chain of zeros, and now you have to move this stack, then you can immediately move them here, saying that these were the next 1, 2, 3, 4 steps of the algorithm. Right? So what we are going to do is simulate the process somehow. In some data structure, we always keep track of which stack we have to move next. You can use a priority queue if you want to. Simulate the process, what to move next. Should be queried. Then we should make a move. When making a move, we can maintain these chains that we can skip by performing some path compression. Okay, if you prefer very standard things, you can apply like disjoint set union data structure to keep track of 0 chains and merge them. But actually, if you understand the concepts more, it's much faster to implement by just implementing a direct path compression. When making a move, use path compression. Or disjoint set union data structure to keep track of the 0 chains, to maintain 0 chains. Okay, and of course we are not fully done yet. We have to somehow answer the question and not mess up the simulation. So what you can do is, this way you can understand that the number of times some stack of beds move to this special vertex is like at most n. Each stack of beds moves here at most once, yes. So you can always maintain the steps made to this vertex independently. You don't apply path compression here. Take steps to 0 or deal with independently of this data structure simulation.
Sorry,
Okay,
what does
and-
it say?
Sorry?
What does it say?
Deal with the steps to B0. B was the array which tells you which hotel is next. So B0 is this node. So deal with steps made to B0 independently. Don't merge them or anything. Keep moves made to this special node, or keep track of moves made to this special node separately, independently of the simulation structure. And what you can try to do now is try to find a state where we can decide whether the algorithm solves the problem or not. How to do that? If the simulation stops, that's easy. Then the simulation stopped, we check whether there is a negative value and answer the question. So if simulation stops, we are fine. If not, we have to find the infinite cycle. Or we have to at least identify that we are in an infinite cycle where nothing happens anymore. The cycle, then nothing changes. Or if you would like to put it in like if you want to use a better wording, you must find whether the same state repeats after some time. And the same state, and for the same state to repeat, you can just focus on finding a state which repeats after we made a move to B0. That's easy to do because you can just because you can just record the last time you were to B0. You don't even need to save the full state. That will be suboptimal because you can make like n steps to this state anyway. So what you can do, for example, is between making steps to B0 at some point or at a later point, you can keep track whether more than one different stacks of beds were moved or merged or whatever. So you can just keep track of whether something meaningful has happened since the last time you moved a stack of beds here. So what we should do is keep track whether something happened since visiting B0 with any stack of beds. Okay, and if nothing happened, so essentially when you had a stack of beds travel from B0 to B0 without anything happening, that you know that you are in an infinite cycle. And one last pitfall that you can fall into is actually finding the answer in this case, because the answer is not the step if the problem is not solved. So if there is some negative value in the subtrees, then of course you just report that is not solved. That's easy. But if we found that we are in an infinite cycle and the problem was already solved, you have to figure out the first step when the problem was solved. And that is not the step when you realize that you are in an infinite cycle. It happened earlier. It happened at a time when a negative value was met with a positive value and became positive. So just keep track of the last time when a negative value disappeared. to find the answer to the question. Value changes. And that's it. I didn't want to give some very specific way to keep track of whether the same state appeared, because that part has like a lot of feasible implementation ideas. That part has a lot of good implementations. The other parts are kind of the same in all solutions. So based on these ideas, you can simulate the process and then find the answer. Yeah. Okay, any questions? Great. Yes?
Lauren has a question.
Sorry, my bad.
When you said path compression, you meant that the parent, for example, the parent of vertex is sent to the parent of the parent or something.
Yes. So you can just be able to merge like paths of zeros that come after each other. So yeah, if something like this happens, you need to update the route or something like that, and you need to keep track how many steps you will make automatically.
Okay.
I have a question.
Yes.
What does it say on the board? Not the last thing you wrote, but the previous one.
This one?
Yes, keep track where.
So just keep track whether something happened since last time visiting B0. So you need to somehow realize whether you just moved a stack of beds from B0 to B0 over a cycle, or whether something else has happened in the meanwhile. So you can just say if any other stack of beds beside the one that last time entered B0 was moved before something enters B0 again, then something meaningful happens, so you should keep simulating.
Yes.
Okay. Okay, further questions? No? So let's move on to the last problem. Okay, it was King Rush or something like that. Was the name, and the idea is that we are given a large chessboard where actually I don't know if it was the rows or the columns, so let's just say the number of columns is not so big. At most, let's say 1,000, but the number of rows can be large. Like 10 to 9 or even greater. Okay, and we are given some queries, some questions when we have a starting position in the first row, we have a final position in the last row, and we have to find the number of ways the king in the chess, the king can get from this to this square. Okay, so a king can move to 8 adjacent squares, but it is obvious that in each step you need to advance one row forward, because I might have not said, but you have to do it with the least amount of steps. So the number of ways to get there using the least amount of steps. Sorry, I might miss that detail. So it can always move to 8 adjacent squares, but of course you actually always need to move a row forward. And so on. Okay, and yeah, we have to answer Q queries, but the value of Q doesn't really matter, it can be large. You kind of need to find the ways to get from one position in the first row to a given position in the last row. Okay, so I think I will explain my approach, or one possible approach. You can immediately see that, or you can just, if you want, you can just play around with it. If you keep track of the number of ways the king can be on any of the squares, you can see that it's a simple like DP. For example, this is 2, this is like 3, this is 2, this is 1, and so on. Okay, for a while it, this is 5, this is 7, whatever. Okay, so there would be some simple DP, and in this like DP solution, you could immediately find the transition, which is, for example, for every position, you can move there from one of the at most 3 adjacent positions, or you can put it in the converse way. From any position, you can move to 3 or 2 adjacent positions. So we definitely have some DP transition. The question is how we interpret it to advance. There are multiple ways. One of them, which mostly relates to the class yesterday, is to interpret it as some kind of a transition matrix. Right? If you consider a vector that gives you like how many ways, or that gives you the starting position, that's kinda enough. The starting position can be encoded as a vector. For example, this means that you started from the second column of row 1. And then the transition matrix is the matrix that corresponds to the DP relation. It should tell you the number of ways to get from the ith column to the jth column in one step. Okay, and this is of course to the first one you can get from these 2. So you add the first 2 entries and the rest is 0. For the next one and all the other ones you can get from these 3 adjacent squares. So to the second one you can get from the first, the second, or the third column. The others are zeros. Okay, to the third column you can get from the second, the third, or the fourth column, and so on. Okay, this is how it ends. Okay, this is the matrix that we have.
So the matrix does
so it gives you a DP update in one row, if you advance one row.
Between rows, and the size is the size of one.
And the size is C by C, right? Because this way we keep track of any possible being in any possible column. Okay. So now we immediately have a naive solution using matrix multiplication, right? Matrix exponentiation, to be fair. So if this is the matrix A, let's say, then the answer is A to the power of R times a given starting position. But since you have multiple queries for different starting positions, it is enough to compute this matrix power and don't care about which exact starting position are you using. Each query will ask you for one specific element from the matrix. Okay, so this immediately gives us a C cubed times log R solution, of course. But this is not fast enough, so we have to find some way to speed up the calculation. Okay, how to do it? You can immediately see that multiplying by matrix A one time is cheap. Right? How to do it? Multiplying by it one time essentially means that you do one DP transition. And so you essentially just use the non-zero entries and calculate the updated values. Okay, and since there are at most 3 ones in each row, this is just ON. Multiplying by A once is just ON because of the number of ones. Okay. On the other hand, you might think that if we are doing this binary exponentiation, then we have 2 kinds of operations. One operation is we need to multiply by A. We already solved that. The other operation is we need to square a matrix. Squaring, and the problem is we need to square the power of A. So we need to square some AK. Okay, because if you consider higher powers of A, they are not sparse anymore. They are filled with entries. So it's not obvious how to optimize it. We should somehow try to use the structure of A to find an optimization to this matrix multiplication. Okay, and there are more ways to derive the solution. One way is try to come up with a combinatorial solution. You can find some bijections between maps, between paths from some row to another row, and these bijections can actually simplify your deal. But we are here to study the structure of matrices, so let me give you another idea. Another idea what you can do is consider some power of A. So let's say AK contains some entries A11, A12, and so on, A1n, A21, and so on, A2n, and so on, AN1, and so on, ANN. Okay? Now, if you would do one step of the algorithm, if you multiply by A, then how does AK plus 1 look like? Well, this matrix gets multiplied by the one-step transition matrix, which means that you actually do the transition for each of the columns here, which means that you will get something like A11 plus A12 if you multiply the first column by the first row. And then you get some similar stuff. You get A12 plus. Sorry, what am I doing? Multiplying the first. Yeah, okay. A12 plus A22. Then you get A13 plus A23, and so on. And finally, you get A1n plus A2n, something like that. And in the next row, you will have something like A11 plus A21 plus A22. No, sorry, A31. Yeah. And then A12 plus A22 plus A32, and so on. So the interesting thing is when you do the transformation with this matrix, you get a matrix like this, you can notice that it still has this shifting structure encoded into it in some way. You can see that, for example, to these values you just add one extra value, and after that you just shift, remove one value, add one new value, and so on. This actually has this shifting structure, but it also has another structure which you cannot see by looking at the numbers. But you can immediately see it if you think about what the problem was originally. Or if you know that, how the powers of this look like, what type of matrix it is. And this property is the symmetry of the matrix. Because think about it, the number of ways to get from the ith column to the jth column is always the same as the number of ways to get from the jth column to the ith column. Any path can be just reversed. Okay? Or if you like the matrices more, this is a symmetric matrix, the powers are also symmetric matrices, of course. So the thing is, this matrix is actually symmetric. This matrix is actually symmetric, even though you don't see it immediately. If it's symmetric, then these two entries are equal. What does it mean that these two entries are equal? Well, it seems like we have a lot of entries here, but remember that this was also symmetric. So the indices are interchangeable. So actually, this term is not here. So this is A11 plus A31 equals A22. Okay. You don't need to immediately see why is it useful at all. Now, if you think about it, we can repeat the same thing multiple times. And you can see that because of the shifting structure, if we move to, for example, this symmetric pair, then what happens is here we shift the indices, here we shift the indices, we get, you can of course expand some terms if you want to, but it is easy to see that you get A12 plus A41 equals A23. Same way, you state that those are equal and you remove the same term. And so on, if you continue, you get an expression for A22, A23, and so on, A2n, something like this. Okay? And then, well, you can see that if you move further, if you start considering these symmetries in this smaller matrix, then you get similar expressions, but starting from the next element here. You don't get expressions for these, but you don't need them because of the symmetry. So actually these are the same. I don't know if you realize what does this mean in the end for the elements of A. AK plus 1 was just an auxiliary matrix that simulated one further step. But what did we obtain about the structure of A to the power of K? We obtained essentially that if we know, somebody was starting to tell something, I'm sorry.
Could you repeat the question?
Yeah, so the question is if we understand these expressions, that we are first getting expressions for these entries in the second row, and then with the rest of the symmetries we get expressions for these entries in the third row, fourth row, and so on. And each of these expressions is something like this. A term marked here is expressed as a sum of two other terms. The two other terms used to express these are, first they are in the first row or first column. It's because of symmetry, it's all the same. Then for the third row, it will be in the second row or second column, it's all the same, and so on. So this means, in the end, that if we knew just one column of this matrix, it uniquely determines the whole matrix. You just need to use these relations to calculate every entry. Right? You can calculate this with a simple sum, calculate this with a simple sum, fill the second row, use symmetry, and then fill the third row, fourth row, and so on. But how much does it cost to calculate one row of a power of A? Well, you only need to do this during the fast exponentiation. So there, what we can do when squaring A, or AK, or AK minus, or whatever, AK over 2, I don't know, to get AK. So what we can do, we can multiply the first column of A, K over 2, first column, which gives us the first column of AK. And then from the first column of AK, we compute the full matrix and proceed. So this is just ON squared, yes?
I didn't get why that relation holds between the coefficients of the power of A. Like, why is that element the sum of the other two? I didn't get that part.
This one?
Yes, why that?
Okay, so here I just show some observation. But if you want to actually prove it, you can just see what two symmetric elements look like in this matrix. I mean, you can just write it for general indices to figure out that you always have something like this. So it's not super interesting. It is something like. I don't know, here the ij, so you just write the element in the ith row and the jth column, which is something like a, what is it, I minus 1, j plus a I j plus a I j plus 1. Except a few entries. And you also write ji, which you obtain by the matrix product, which will be something a bit different. So it will be something like, I don't know, it's essentially the same formula. You just have to take care of the corner case when there are actually two terms. Sorry. So by the same argument, this is like j minus 1 I plus a j I plus a j plus 1 I, something like this, and then you just need to realize that these two are the same. And I'm just thinking about which entries do you already know. So
The first one is
yeah, so if you sorry, yeah.
the first one is A plus 1 and J. The first equation This one.
This is a, this one is a I plus 1 j. Okay, so here, here if you proceed iteratively, you always know. Yeah. You have to realize that if you evaluate iteratively, these two are already known, and from these two,
maybe you can prove it by induction, or like if you know that if the previous power satisfies that, then multiplying by a.
I mean, you also know, I mean, if you just do it for one of the triangles, like the upper half or the lower half of the matrix, then depending on which half you do, you also know one of these. If you like switch the index, so you can just assume that you know this one and use the relation to calculate this one by saying that you do this for the entries where. Like j plus 1 is greater than I, or greater or equal than I. Yeah, so it can be given like a simple general formula as well.
I'm sorry, I
Okay.
don't understand the notation and the lower left corner.
Here?
Yes.
Okay, so here this is. So here this is the first column of the previous matrix, the previous power. If you multiply the first column by the matrix, then you get the first column of AK.
Yes.
So it's A to K first column. And then starting from the first column, you do this process to find the matrix.
Okay, fantastic, thank you.
Okay. Yeah, so this solution in this form, but also in the other form. So, even if you start doing combinatorial arguments, you can find some useful relations that you can try to turn into a formula like this. This also seems a bit ad hoc, though this trick is known, not too common in competitive programming, that you try to make a mock step just to find relations between the elements of a matrix. But actually, like how to even find the idea of this solution? Well, you can just think about it. Your problem essentially is to find how the higher power of A look like. So you can just use your computer and calculate like the 7th and 8th and 9th power or something like that, some non-trivial power of a relatively small case. And it's relatively easy to see the relationship between the number. I guarantee if you put it into Wolfram Alpha or whatever, do a matrix exponentiation, you can immediately spot a pattern. And actually, the fact that the idea, so the idea itself might be also familiar if you ever took a look at higher powers of the matrix of the Fibonacci sequence. I don't know if you ever noticed, but actually for the Fibonacci sequence, if you take a higher power of the matrix, it actually always contains several Fibonacci numbers. So, for example, for the Fibonacci matrix, even though it doesn't make any sense in terms of computation, but the same trick can apply to Fibonacci sequences. Since you know that each term is a Fibonacci number of some given index, you can easily prove it inductively. You could actually construct the matrix of a higher power. You can easily construct a higher power of the Fibonacci matrix by computing one column, doing a matrix vector product, and then just fill the matrix, knowing which Fibonacci numbers does it contain. So finding similar relations is actually pretty common, though it's not common in like programming contests. And also, of course, This is not the only way to figure it out, but this is like the most elementary way. You just look at the higher powers of the matrix and discover a relationship which speeds up your calculation. There are, of course, other ways to do it. For example, you could see that the dp transition itself is like a relatively small recurrence. And it's actually a kind of linear recurrence, though it depends on multiple indices. So you could try to, for example, turn the recursive relation into a generating function and proceed that way. That's also feasible. It's not obvious how to do it. So this solution is also not obvious. That solution is also not obvious. But there is like a good starting point you can build upon. Or there is one more trick. I'm not sure if I will talk about it on some other day, but you can also derive some useful relation if you know the so-called Cayley-Hamilton theorem for matrix powers. So that's also a feasible way. I might talk about it on some other day, but probably not today.
I'm sorry, what's it called?
So it's called Cayley-Hamilton theorem. Okay, yes?
This is when you find the characteristic polynomial.
Yeah, so the theorem itself, of course, if you know what is a characteristic polynomial of a matrix, then the theorem itself is deceivingly simple. The theorem states that if you substitute the matrix into the characteristic polynomial, you get 0. Deceivingly simple in the sense that actually this is very difficult to prove. I mean, it requires some deep ideas, or it can be also proved using, for example, generating function ideas. But anyway, so this is a relatively deep theorem, but it's also often useful if you want to get something for higher powers of matrices. Okay. Why is it useful to do that? It's useful to do that because in the end this is a polynomial. So you can somehow try to perform polynomial exponentiations or other operations, but you usually need to be careful and find some ideas, because if you just take the powers of the polynomial, it becomes bigger and bigger. So you cannot just compute the 10 to the power of 9th power because it contains too many entries. So you somehow need to truncate it using some observation or other relation. So it's not a cheesy way in the sense that it's not easy to carry out. Okay, who solved the problem? How did you solve it?
Using Cayley-Hamilton.
Yeah, that was my guess. I mean, I just briefly looked and in the code I only saw the polynomial operations, of course, but my immediate guess was that it was based on the Cayley-Hamilton. So that's a good way. Okay, nice, good solution. Okay, let's just have the break. I think it's time.
See you tomorrow.
Okay, welcome back. Let's continue with the second part. Okay, we will move on a bit. So I promised that I will finish the topic with convolutions that we started yesterday. So I will start with that, and we will see whether we have some time left after doing it. So yeah, before that, so if you were wondering, because there were, I think, like 2 people asking it, so in the first part when I explained the winning strategy for this game on the plane, I actually proved that some positions are winning in that graph, but I didn't prove that the others are losing, which is actually very simple, but I forgot to mention it. If you consider every other position, so on the even levels, then from the even level you have to move to an odd level, and you can apply the strategy stealing argument that the guy who moves from that level is losing. So it's kind of obvious that that on the other levels every position is losing. Okay, sorry about that. So let's move on. We were discussing the OR convolution, as this is one of the more simple ones. We described like what kind of transformation are we looking for. The main idea is to perform the convolution. We do a linear transform where computing the convolution is equivalent to computing the product of the 2 arrays, and then we need to move back. So and I stopped at the point where we wanted to invert the linear transformation that we use for OR convolution. And in the OR convolution, you can remember that the transformation itself was this sum over subset type of convolution where you have some, let's now notate it by CK. So when some CK is transformed to the sum, the sum of some entries in the array where the bit representation of I, the index, is contained by the bit representation of K, right? This was the transformation. We found the matrix, found an efficient algorithm, and we know that the product works instead of the convolution. So we have everything except the inverse. So we have everything except the inverse. I mentioned that you can find the inverse by similar means if you want to. You can try to figure out the matrix, do something, but you need to come up with an idea to revert this, and the most elementary way to do it is probably by using the principle of inclusion-exclusion. So for example, if you consider something like if you consider that this C prime K contains the sum of these terms, and you want to get one specific term, which is the CK term, that's one term in this summation, right? Then how can you do this? Well, all of the terms in this C prime contain the sum of several C entries. So you could do something like, for example, if you have a very simple case like C2, then you can, if you want to recover C2, you can do something like take this sum of C2, which contains the indices 0 and 1, 0, these 2 indices, right? So here what you can do is, since this 0 index term only contains itself, so from C prime 2 you can just take C prime 0. And you don't need to do anything else, because this way you removed from this all the ones that are contained by a real proper subset of K. Okay, this is the only proper subset. So if you remove those terms, you are done, right? But on the other hand, if you consider recovering like C3, then you actually have multiple proper subset of bits. So in this case, if you start by C3, then the actual proper subsets here, okay, we of course have 1, 1. This is not a proper subset, but we still have we still have like 1, 0, 0, 1, and 0, 0 as subsets of bits. And you cannot just, of course, remove each of them because of the fact that if you remove like C prime 2, then it also contains the 0 index as here, right? And the same is true for C prime 1, which also contains the 0 index. So it means that if you try to remove these guys, then you actually removed the terms corresponding to 0, 1, and 1, 0, but you also removed the term 0, 0, and you removed it twice, once here, once there. Okay, so this is how the principle of inclusion-exclusion comes into picture, because now you have to add C prime 0 once more. Okay, and that's kind of how you do it if you would like to, but I think it was done last week, so I don't really want to take much time in it. You can just draw the containments between these sets of bits, so you can see that in that graph structure. To compute this one, you can take this, then subtract everything that differs by 1 bit, but then you removed everything that differs by 2 bits, more than once, twice, so you add them, and then you have to do it recursively because the same transfers to the indices with less number of bits. Okay, so you can just think about it as always removing 1 bit and moving down. Okay, so this was just to repeat how the idea works. So it turns out that if you think about it, this inclusion-exclusion transformation also has a matrix. You just have to take indices which are contained by the current index, and you either have to add them or subtract them, depending on whether you currently have them 1 times or -1 times in your current sum. So that way you can get rid of them. And you can immediately see that the matrix must be then very similar to the matrix of the original transformation. Remember that yesterday we talked about the matrix of the original transformation, which was the sum over subset matrix, where you get ones at each position which contains the bit representation of the previous element. Yeah, something like that, and so on. Okay, so now it is imminent that in this case we get the same entries, just some of them will be negative ones, right? And you can find the same recursive nature of this calculation in the sense that recursively speaking, you always need to just remove 1 bit. So if you already know the matrix for some size, then you can consider adding 1 extra bit to the front of the number. Okay, and realize that if you add an extra bit to the front of the number, then if you keep that extra bit in the containment, then for the lower position, the same thing repeats. The same containments repeat, and you keep the first bit. Otherwise, if you don't keep the first bit, you will need to remove something. No, if you don't keep the first bit, sorry, then you removed 1 bit already. So that means that for the lower position, the signs will flip because they will contribute to the reverse sign operation over the sum over subsets, right? For this part, you already removed 1 bit, so whatever you need to do here will be multiplied by -1. because those were taken by the higher bit. So this one flips signs, so it will be like even something like this. You can easily verify that it's correct by looking at those examples. It's correct. Okay. Yes.
So, like the matrix, the ith row is the coefficients of the C primes. Like, for example, the first row.
Yes, so now what we are doing here is we are reversing the transformation, so these are the C primes.
Right, and the answer would be the C.
Yes,
Okay.
yes.
I didn't quite understand like the version of the matrix.
Okay, so
So the,
so if you remember the argument from yesterday, it was a bit more simple because there to find the containments you could just consider the case when you have some submatrix and you add an extra bit, which means that the size of the matrix will double, right? And you just have to consider what happens, what do you do with the extra bit? Okay, and in this case, when we are doing the reverse transformation, what you can do is either consider indices where you keep the first bit. Then for the lower bits, you can consider exactly the same containment as if there was no first bit.
right, yes.
So this part is repeated in the matrix. This is the same. Okay, and in this case, you decided to remove the first bit, the extra first bit, so that means that in the inclusion-exclusion, everything which is contained in the number after removing the first bit is explained here, but it gets multiplied by -1 because then it changes sign in the exclusion.
And this new matrix, and this new matrix is also the inverse of the original matrix, no?
Yes, yes, by construction, this is the inverse of the original transformation matrix. Yeah. So essentially that's it. You can see that we can apply the very same argument, but we have to realize that there is some exclusion in the background. But we can apply the same inductive argument to realize that this matrix repeats the pattern, and this is how it's done. Okay, so now the structure of the matrix is like Tn0, negative Tn, Tn. And with this we can perform a similar divide and conquer, but you need to be careful because it's not exactly the same because of this negative sign. And of course in the sum over subset DP you also need to change some addition to subtraction to get back the original entry.
Well, like if we're modeling it as a subset DP or subset SOS DP, then like the order in which we traverse information doesn't matter. Like we just have to replace the minus with the plus, or the plus with the minus.
Yeah. So there you don't do something like compute the inclusion exclusion as it is. You just use the fact that if you do that iteration, the terms until the very end will still contribute to some sums over some subset of indices. So that's like flattening out this divide and conquer and do it iteratively.
Fantastic.
Okay, any questions to this? Great. Okay, of course, so if you want to, you can actually derive end convolution the same way. The matrices are almost the same. There are some small flips, but if you want a bit of a practice, you can easily derive the end convolution and have a very, very similar algorithm. Because of course you know that in the other approach, in the DP approach, the algorithm is there. It's also very similar. You just have to swap some orderings essentially. Okay, so this is left as an exercise. If you want to, you can do it. Okay, so of course, this type of matrix that we encountered here, you could see that here the inversion kind of depends on the principle of inclusion-exclusion, and it is well explained by that graph structure that Franek was talking about the last week, which he actually used to find the iterative algorithm. Okay, so there are these kinds of convolutions which have this property. There are a few additional ones beside these two. For example, I don't know if you know, there is something which sometimes called GCD convolution, or it is something like the similar to the classical Möbius transform. I don't know if you are familiar. So this is a transformation where you have some AK, and then what you do to transform this. So the convolution itself, you have once again AI, BI, two vectors, and you want to compute the following convolution. CK would be the sum of AI times BI, where we have the GCD of I and J equals to K. Okay, actually there's a huge amount of number theory problems that uses this. It's not too common at, for example, ICPC, because of course the contest itself doesn't want to use like an extensive amount of mathematics. But I don't know, for example, if you try to solve some mathematics related problem efficiently using the computer, this is actually very common that something like this comes up. So this is what you could call the GCD convolution, and here you can actually explain it and find some algorithm by considering a similar graph structure as what you did for the sum over subsets DP solution. Okay, in what sense? In the sense that you could create some graph of where the edges corresponds to divisibility. Okay, and then approach that way. I don't really want to go down that way, because this was intended to be more of a remark than an actual area that I wanted to investigate. But so since many of you don't know this one, so the main idea here to perform the convolution is very similar to that, which means the transformation we want to apply. So we want to transform AK to A prime K, which consists of the sum of the AIs, okay, where, which one is the correct, you could consider two kinds of containments. Where K divides I think that's the correct for this one. Yeah, I honestly don't know by heart, because the other one also makes sense. So without deriving it, I'm actually not sure. After deriving it, I know this. The other one where you would transform AK to A prime K equals sum of AI, I divides K. Okay, this also makes sense. This is actually important when you do the other one. Can you guess? LCM, yes. Yes, you know that there are close relations between GCD and LCM. For example, the product of the two is equals to the product of the two numbers, so it is kind of natural to realize that there must be an LCM convolution, which is something similar but over the least common multiples. Okay, yes. Yes?
What's the indices on the A plus A prime equals 1k is divisible by I.
This you mean?
No, the one above it. This one.
This is the linear transformation that can be used to compute this convolution. Sorry, so this is I'm just using like the same methodology as I explained yesterday. So this is the convolution we want to compute, and this will be the linear transformation, and we want to do this linear transformation for A and B, and we claim that after the linear transformation, we can take the product of the element-wise product of the transformed vectors to find the transformation of the CK which we are looking for. And then we just need to do the inverse transformation to get the result. Okay, so that's what I mean by these notations, the ideology that or the algorithmic scheme that we described yesterday.
The two transformations you wrote are different. Or
Yes, in one of them k divides I,
yes,
and in the other one I divides k.
but in the left term they are the same.
Which left term?
I mean the left part is A plus A prime.
I actually don't understand what you mean.
I think
I don't understand the difference
like a
between the
plus.
two equations.
Where AK and A prime K, I think it looks like a plus sign there in the middle, but it's not.
Yeah. I mean, I don't have plus, but I.
The derivative.
This one?
Yeah.
Oh, okay.
Yeah.
Yeah, sorry about that. So that's the transformation. Same as here. Yeah, okay, sorry. Yeah, so actually, if you, I don't know how far we want to go here, but actually, if you look at the matrix here, it's an interesting matrix. So if we allow zero index, it's perfectly feasible. Just in some problems we discard zero. We sometimes don't want to deal with zero in terms of divisibility. Then the matrix is here. So on the first row, all of the entries will be ones, because you know that k equals if you think about it as like what is it, like every k divides zero. Okay, in the next row it will be every second element. It might be zero at the end. It doesn't matter. In the next one it will be every third element. It might end with zero. Okay. This will be the transformation matrix because these will be the indices that we add, right? For k equals 0, okay, the first row is for k equals 0, you could say that, okay, their division holds for every index, or k equals, I equals 0, sorry. Yeah, for the next one, k equals 2. What? Sorry, yo. So I'm confused. Okay, yeah. This is some A matrix. Okay, and we are computing the kth entry A prime. So sorry, maybe we don't want to consider 0 at the end. Maybe it's easier. Yeah, maybe it's easier to just index from 1. Yeah, because then if k equals 1, yeah, for k equals 1, it divides every index. So we add for every index. Yeah, now it makes sense. For the next one, if k equals 2, then it divides the second, the fourth, the sixth, and so on indices. So we add those. Okay, for the next one it divides if k equals 3, so it divides the third, the sixth, and so on index. So it's every third element and so on. Okay. Yeah, it's diagonal. Okay. So you see that it might be tricky if you wanted to find the same kind of repeating pattern here. We have some repeating pattern between the rows, but we don't have the same kind of repeating pattern that allows us to multiply by the matrix with divide and conquer, right? So actually here, the idea to do the multiplication, the transformation, is actually much more simple. Yes?
To sum all of the numbers, then all the evens, then all the multiples of 3.
Yes, you just have to realize that this is actually a sparse matrix, even though the first few rows doesn't give it away. In the first row you have n ones, in the next one you just have n divided by 2, n over 2 ones, n over 3 ones, and so on. So actually here the transformation is just naive multiplication. Which is O(n) log n, because the number of ones is like n plus n over 2 plus n over 3 plus and so on plus 1. Okay. Okay, and so up until this point, of course, there's nothing tricky, but if you want to invert it, you should once again realize that the inversion can be done using the principle of inclusion and exclusion. So you can try to remove different numbers or different sets of divisors in some sense. Okay, and you can also do some speed ups if you construct prime numbers by some sieving and so on. So this is a topic you can dwell into. I didn't really want to give much detail about it, but you should notice that these two convolutions also work the same way. On the higher level and on the lower level, you need a different algorithm to perform the multiplication efficiently. Okay, of course I didn't prove, but you should still prove that like after the transformation, the product of two entries, the product of A prime k times B prime k is the transform of C prime k. That's actually not so difficult to do. It's like more difficult to come up with the transformation itself. Okay, anyway. Yeah, very briefly we can also talk about the FFT, I guess, where we actually want to calculate the convolution which gives us the sum of, or the product of AI times Bj, where I plus j equals to k, where once again the main idea is not so easy if you just want to find like what linear transformation you should use, because here, well, of course, the main idea comes from the idea of multiplying polynomials where the coefficients are like this. So actually, as you already know, this sequence is the sequence of coefficients of the product of two polynomials with coefficients a and b. You already know that. So actually, you might interpret all of this problem as in terms of polynomials, and you need to realize that if you want to compute the coefficients of the product polynomial, then actually it's not so hard to realize that what transformed arrays would do it with pointwise multiplication. Okay, I hope you know from last week, it's the transformation where you, instead of taking the polynomial by the coefficients, you take it by values at some points, right? Because if you express the polynomial at some points, then the value of the product polynomial at the same points will be the product of the values, and that's it. So in this sense, it's easy to realize that the linear transformation should map the coefficient vector let's say a0 and so on, an minus 1 to point values a prime plus a prime and minus 1. Yeah. But this is still like this has a lot of freedom, right? I mean, you could for the linear transformation you could just choose any set of points, do the linear transformation, and then do the product and go back. The problem is it's not necessarily easy to come up with the points themselves such that the matrix used for the transformation has a structure which allows like a quick transformation. So the problem is we want to choose the point where we take the point values in such a way that fast calculation can be performed, right? Okay, and so what we usually, I think we shall just rely on the lectures from last week. You already know that one feasible idea to do this is to consider either like the roots of unity or over the complex domain, or just take some field or maybe just a group structure where you have some cycles according to multiplication. So you could find multiple structures that have a favorable that give you favorable properties in the sense that powers of the points where you evaluate the polynomial repeat in some pattern. Usually that's what we are looking for. So one particular idea was that we can use these roots of the unity, right? So 1, v square, and so on. You know that for these values on the complex plane, multiplication is just a rotation around the origin, so the product itself move around with equal angles. Right? Yeah. Okay, so if you think about it, if you choose v values like this, for some vn equals to 1, then the transformation matrix is actually relatively simple, because you want to evaluate the polynomial at some point like this. So if you think about a polynomial with these coefficients evaluated at some omega to the power of k, then it will be some powers of omega, of course. It will be some like a0 plus a1 times omega to k, and so on, plus an times omega to n times k, something like that. Minus 1, but whatever. So in the end, you can see that the matrix itself how does it look like? Okay, so you see that each coefficient is multiplied by a power of omega, and you can think about the different values of k, which will correspond to the different indices in the resulting vector in a prime k. So first you have to take like the zeroth power. If we index from 0, that will be 1 for each power. So you need 1 time a0, 1 time a1, 1 time a2, and so on, 1 time an minus 1. Okay, this will be for k equals to 0. Right? Okay, and for an arbitrary row, you can see the coefficients here, the coefficients of the a's, like 1, omega 2k, and so on. Okay, but just to be able to realize the matrix structure, you should see that the next one is 1 omega, omega square, and so on, or omega to the power of n minus 1. In the next one, you use omega square, so it is 1 omega square, omega 4, yes, and omega 2 times n minus 1. Okay, yeah. Okay, and so this goes on. This goes on somehow like this. So this has several symmetries to be used, but the one particular which gives the classical algorithm to compute the transformation, the Fourier transformation fast, is actually very similar to what we did for the OR convolution and AND convolution, so the first few examples, where the idea was that we should perform the matrix vector product somehow blockwise so that we can use divide and conquer. So we should break down this matrix somehow into blocks that exhibit some symmetric nature, right? So one particular symmetry that you might use has two observations regarding the roots of unity. One observation is that you can see if you, not just row-wise, but also column-wise, if you want to move to the next column, then in each entry you multiply by a power of omega. More specifically, if you want to get from any column to the next column, you just element-wise multiply by this 1 omega, omega square, and so on, omega n minus 1 vector. Okay, element-wise. This gives you the shift from one column to the next column. Okay, and another kind of symmetry that you can see, maybe that's the easier one to see, to be fair. The other symmetry that you could see is if you try to break this matrix into two halves, where in the lower half you can see that powers start from the index n over 2. Right? I mean, here you get something like omega 2 n over 2, omega 2 n over 2 plus 1, and so on, and this pattern repeats. Okay? So that means that in the lower half, you can interpret it like the elements are multiplied by omega to the power of n over 2, which, if we want to do this for the powers of 2, sizes of powers of 2, just to be able to reduce the size to half, then omega n over 2 is always negative 1.
I don't know.
Yes?
That wouldn't it be omega to the power n divided by 2 times k? depending on the column you are. Like the first column is always 1.
I mean, not for every column, but this is for the first column. And then the rule itself is the same. So here, of course, this will be multiplied by 2. So it can be interpreted as like, so if you want to interpret it, it's better to do it by saying that so if you consider a column contains these. The column contains powers of these. So all of these will be, depending on the index of the column, will be raised to the 0th, 1st, 2nd, and so on power. So these are raised to some, let's say, jth power. Okay, and what I mentioned here is if you expand it to all of the columns, it just only applies for the inner term. So these guys in the lower half will be omega n over 2 to the power of j, omega 2 n over 2 plus 1 to the power of j, and so on. Okay, and now it is clear that this omega 2 n over 2 equals to -1 only applies to the base number. So these numbers are actually the same as like -1, negative omega 2 1, and so on, negative omega 2 2, and so on, negative omega 2 n over 2, raised to the jth power.
Right, so it will be negative there.
So that means that if you consider all columns, then it means that the columns in this lower half flip signs, alternate between -1 and +1, compared to the top part. Okay, so we actually want to use these two symmetries. Using the second one is kind of obvious in the way that it breaks the matrix into a top half and a lower half. So what we will do is we will multiply the vector with the elements of the top half, and we won't need to do the same with the lower half. Okay, but what about the other one? The thing here is actually there is one hidden relation, which is why it is useful to spot that the columns are multiplied by this. This hidden relation is, if you think about reducing the problem to half size, if you reduce the problem to half size, you not just reduce the vectors to vectors of half the size, but you also reduce the size of the matrix such that omega is essentially replaced, omega is an nth root of the unity, let's say, omega is essentially replaced by omega square, an n over 2 kind of unity, or a root of unity. Okay, not the nth, but n over 2, n over second root of unity. Okay, so that's why it is actually useful, because if you think about this relation between the columns, then you can easily see that you should actually try to exclude the odd columns and consider only the even columns, because the even columns contain the even powers of omega, and omega squared will be an n over second root of unity after reducing the size of the problem. So now finally we can say that the symmetries we found is we should have this part of the matrix containing only the even columns. Okay, up until the half size of the matrix. Actually, the last one is excluded, so I'm minus 2. Okay. So this is the matrix that we get if we only consider the top part and only the even columns. So you can immediately see that this is equivalent to the original matrix, but for omega square. So if this matrix is for size n with omega, then this will be for size n divided by 2 for omega square. So you should just consider omega square instead of omega, and you get the same problem reduced to half size. Okay. And be careful, because if you want to solve this problem, you have to solve it for what entries from the vector? Which entries? Only for the even indexed ones, right? Because the first column is multiplied by this, the third column, the next even column is multiplied by this. So the terms corresponding to the odd columns are skipped. So we need to multiply it. We need to multiply it by A0, A2, A4, and so on. Like this. Okay. Right? Now we just have to figure out what to do with the odd part, with the elements with odd index. Okay, and for those, you can consider the part of the matrix that deals with the odd indices. If you only consider the part of the matrix that deals with the odd indices, you can easily find that it is the same matrix, but each column is multiplied by this vector element-wise because of this relation between the columns. Right? So you can say that for the odd part, this is for the even part. For the odd part, it is actually the same matrix. It is actually the same matrix, but element-wise multiplied by this 1 omega, omega square, and so on, omega n minus 1 vector. Right? So it means that this is for A1, A2, and so A3, and so on, A n minus 1. So it means that what we can do is we can perform this transformation and deal with this later, because this is just an element-wise multiplication, and the result of this is a vector, so it is linear. It takes only linear time to do that. Okay, that's what we do. We essentially divide every entry of the matrix by the corresponding number and multiply by it later on to get the correct result. So finally we know how to do this, right? We actually need to do this transformation for the even part of the matrix. We have to do this for the odd part of the matrix. That's the divide and conquer part, the recurrence. And after that, we just have to assemble the original result. To assemble the original result, we have to notice that the odd numbers, the odd indexed vector, has to be element-wise multiplied by this. And after that, we also need to make sure to construct the. After that, we also need to ensure this flip of the signs, which means that So okay, sorry. So which means that after getting back the result, you can assemble the top half of the vector by just taking the results, and for the odd elements, multiply by the corresponding root of unity, and for the lower for the others, you also have to multiply by negative 1. Am I correct? Just want to look at. Yeah, okay, that's it, right. Right, so for the lower half of the matrix, you have to multiply that part by negative 1, right? Okay. So this is a bit more tricky symmetry to find a divide and conquer way to compute this transformation. It relies on similar ideas, of course, as the previous one. The complexity works similarly. You reduce to the same problem of half size, and then you do ON operations depending on the current n to construct the result and return it. So it's the same recurrence, and so this is O n log n. Okay, yes. Okay, so to kind of wrap up this topic, there is, one more transformation, and let's just do it briefly, because actually the idea to construct the transformation itself is not so difficult. That is the XOR convolution, where you want to do ck equals like ai times bj, where the XOR of I and j equals to k. Okay, so this one is actually kind of hard to come up with this in a natural way, because it was kind of invented in the reverse way. I mean, there was a construction for a linear transformation, and it turned out that it has this tricky property for the bits. So because of the way it was invented, it makes it kind of hard to argue for it in the converse way, where you explicitly say, yeah, here I am and I want to calculate this. Oh, this is a difficult problem approached from this. So that's what makes it a bit tricky. On the other hand, there is actually a recursive way to build up this transformation, and it relies on the following. I don't know if you ever noticed the following algebraic property. If you do like a0 plus a1 times b0 plus b1, then you get A0 B0 plus A1 B0 plus A0 B1 plus A1 B1, right? But if you do this with subtractions, then you get A0 B0 minus A1 B0 minus A0 B1 plus A1 B1. Okay, notice that if you do this with subtraction, then the sign of the entries will actually depend on we just have one bit, but depends on the XOR value of the bits, right? If the XOR is 1, this is negative sign. If the XOR is 0, then you get a positive sign, simply because of how the signs change depending on the indices. Okay. So, and the thing is, if you look at these two formulas, then there are actually two ways to cancel out terms here. Right? One way is to add them, that removes the odd part, and one way is to subtract them, that removes the even part. Okay. Can you see the relation between the two for one bit? This is actually what we wanted to compute for k equals 0. And this is what we wanted to compute for k equals 1. Right? Pretty simple. Okay, also, you can notice that what we did to the two numbers, A0, A1, is in one of the two multiplications, we added them. In the other one, subtracted them, and we did the same to B. Right? Okay, and so it turns out that what we did here is we had two entries, added them, subtracted them, then we multiplied, then we, surprise, surprise, added them and subtracted them. So actually this linear transformation is inverted here. And we performed the convolution after transformation by multiplying entries. Okay, this works for one bit. It kind of relies on this algebraic identity, which you can of course express in terms of group theory, but there's no real point of doing so. I mean, this is something that many people observe during their elementary school studies. Okay, so how to use it to our advantage? Well, we will expand the same transformation to multiple bits. How to do that? Use the same argument as we did for the OR and AND, so the first few examples, right? For one bit, we already know what to do. For multiple bits, we can consider the same kind of bit removal and adding arguments. So it turns out that it has the same block recursive structure. You have to repeat this kind of thing similarly to the inclusion-exclusion principle, but otherwise it's pretty like natural to see it. And that's it. We solved the problem. We didn't need anything, kinda. I mean, on the way, we actually solved the issues that were encountered during other problems. I mean, this way, we not just see that we get this linear transformation matrix, after which we can rely on these identities to verify that the product will give us the transform of this. Of course, in the induction, you need to be a bit more careful. So the induction is not like one sentence proof. You need to look at the induction a bit more carefully. I'm not denying that, but otherwise it works. And what is really good is that we immediately proved that in the end, to invert the transformation, you just perform it again, but you have to realize that the result will be multiplied by some number. So if this is Tn, then the inverse then the inverse is Tn once again, but divided by n. Yeah. Something like that. Okay, because you see that if you transform, then you transform back, everything gets multiplied by the number of times they occur. Okay, kinda that's it. This is how you can like separate the bits and come up with the idea using an elementary argument. Of course, as I said, this kind of relation is kinda natural over fields with two elements. So of course, it is very popular to explain it using some more deep algebra, but that's why it works and that's how it works. Okay, so that's it. Sorry for keeping a bit longer, but we also couldn't keep up with the starting time. So I hope that you are not angry or annoyed about it. Okay, so thank you for your attention. Yes, so good luck at the contest. Tomorrow we will continue and we will consider some different topics. Okay, thanks.